Hi, my name is Yuka Wing, and I'm excited to present my final year project titled Development of a Real-Time Safety Detection System for Human-Robot Collaborative Workspace for ELV Dismantling. In this project, the poster is divided into 4 main sections: Introduction, Methodology, Result and Discussion, and Conclusion. I'll walk you through each and highlight the system performance. End-life vehicles are increasingly being dismantled for recycling and remanufacturing, as industries strive for sustainability. However, dismantling involves close interaction between human workers and machine. Traditional robotic systems are often not designed for collaborative environment, making it unsafe for human-robot shared tasks. This project proposed a low-cost real-time safety detection system using a single webcam, YOLO V8 instant segmentation, and media pipe hand to monitor and detect proximity between robotic joint and human hand in real time. The system enhances safety in collaborative environment by issuing real-time alert when hand enter a defined danger zone. The goal is to prevent collision and enhance safety during ELV dismantling. There are 3 key problems that this project addresses. The high safety risk manual ELV dismantling process exposes workers to physical hazards such as cut, heavy lifting injuries, and contact with hazardous fluids. Conventional robots lack the adaptability and safety features needed for dynamic human shared workspace and high-cost existing sensor-based safety system. Thus, there is a critical need for a cost-effective and adaptable safety monitoring solution that can work in real time with minimal hardware. This project is guided by 3 research objectives: to develop a real-time detection system that identifies both human hand and robotic joint using YOLO V8 instant segmentation and media pipe, to implement a safety response system that estimates hand-to-robot distance and prevent potential collision, and lastly, to validate the performance and safety of the detection system through real-time testing. The hardware users includes the MyCobot 280 M5 robotic arm and a Logitech C270 HD webcam mounted to capture the workspace. The software framework includes YOLO V8 for detecting robotic joints using instant segmentation and media pipe hand for detecting and tracking hand landmarks, particularly the index fingertips. A custom dataset was prepared using image of the MyCobot arm in multiple scenarios. 5 class labels were defined for each of the robotic joint. The YOLO V8 N segment model, which is the lightweight nano version of YOLO V8 for instant segmentation, was used. The training was conducted on a laptop with an NVIDIA GTX 1650 GPU, and RoboFlow was used for annotation and preprocessing. To determine the most effective camera angle, the system was tested using front, top, and side view. Each angle was evaluated for visibility and detection accuracy of hand and robotic joint tracking. Each frame captured by the webcam is processed in real time. YOLO V8 identifies the location of the robotic joint, while media pipe hand tracks both the left and right hand of the operator. The pixel distance between the index fingertip and the center of each detected joint is calculated. Then, using a known reference width of 4 cm for the joint, the pixel to cm ratio is computed to estimate real-world distance. The pixel to real-world distance conversion formula equation used is where dp is the pixel distance between fingertip and robotic joint. WPX is the bounding box width in pixel, and WCM is the known physical width of robotic joint. If the estimate distance is less than 5 cm, a danger flag is raised, a warning sign is played, and the event is logged. The system records the detail like distance, class, detection, confidence, and in an Excel file for future analysis. To evaluate system robustness, we tested the system at 3 fixed distances: 70, 80, and 90 cm between the webcam and the robotic arm. This helps assess how proximity influences detection precision by measuring both hand and robotic arm confidence level along with pixel-based distance estimation to determine the accuracy. The front view was selected as optimal because it provided a clear view of both hand and all robotic joints, minimizing occlusion and enabling more accurate landmark tracking compared to the top and side view. Here is a comparison between single and both hand detection. The detection accuracy was highest at 70 cm, with the lowest mean absolute error and highest confidence for both hand and robotic joint in single hand testing. Mean absolute error was used to quantify the pixel distance deviation between the actual and estimated distance, with 70 cm showing the most reliable readings. As the distance increased to 80 cm and 90 cm, the mean absolute error increases, indicating a drop in precision due to the smaller object appearance in the image, which made it more difficult for model to tightly fit the bounding box. Accuracy decreased at 80 cm and 90 cm due to reduced image resolution and pixel density, affecting bounding box accuracy and confidence score. Both hand detection at the same distance exhibit even higher mean absolute error and lower average confidence compared to single hand detection. This difference became more significant beyond 80 cm, where smaller pixel scales made distinguishing between overlapping or nearby objects more challenging. This performance degradation was primarily due to increased number of detection object instances during both hand testing, which increased the complexity of the detection. This can cause the model to struggle with close proximity object separation, reduce accuracy, and increase false detection or bounding box shift. Nevertheless, this system successfully issued danger alert when the hand entered 5 cm threshold, and all relevant performance metrics were logged for analysis. Here is the performance analysis of the YOLO V8 training model. It is trained across 5 joint classes, demonstrating strong performance and achieving a mean average precision of 0.971. This value indicates high overall detection capability across the dataset. Our highest precision recall score reached 0.994 specifically for the third joint, reflecting excellent model consistency and classification reliability. Even the lowest performing joint maintained a 0.94 score, proving model robustness across different lighting and orientation conditions. In conclusion, the real-time safety detection system successfully detects both human hands and robotic joints in real time using low-cost hardware and open-source tools. Experimental testing confirmed highest accuracy at 70 cm in the front wheel, with reliable danger alert triggered within the defined 5 cm threshold supported by the YOLO V8 instant segmentation model, which achieved a high training accuracy of mean average precision for robust robot joint detection. The system demonstrates its potential for safe and cost-effective human-robot collaborative in ELV dismantling. It offers a practical and low alternative to traditional safety barrier or expensive sensor by using only a single webcam and readily available deep learning framework. Lastly, I would like to sincerely thank my supervisor, Associate Professor Dr. Raja Arifin bin Raja Ghazali, for his guidance and support throughout this project. I also like to thank Mr. Gunn and the staff at the Center for Product Design and Manufacturing for their help with lab resource and equipment. That's all from me. Thank you for your attention.